Okay, we return to our quest for knowledge. We are studying linear systems like this, where y prime is a times y, a is a 2 by 2 real valued matrix. We're looking at the case where we've got just one real eigenvalue. If a is real valued and we had a complex eigenvalue, we'd have to have two of them because they have to come in conjugate pairs. But we're only able to find one independent eigenvector. Now, in the previous video, we looked at a particular example that was partially decoupled, and we got this as our answer. So I'm going to use that to make an educated guess that in this situation, this is definitely a guess at this point, the general solution is always going to look something like this. That we're going to get y equals e to the negative 2t times some vector plus t e to, it won't always be negative 2, I'm sorry. Negative 2 was the eigenvalue in our particular example. E to the lambda t times v naught plus t e to the lambda t times v1. So rather than expressing this as an arbitrary linear combination of two known vectors, I'm saying I'm going to have a combination of these two functions with these two unknown vectors. Okay. And I'm kind of hoping, in this case, you'll notice that this vector had two components, c and k. Once I knew those components, I completely knew this vector, because it was built using the same components and then just a 0. Okay. So, in fact, I'll give it away. It's going to turn out that if I'm able to get this vector, I can describe this vector always in terms of the other one. But what we're going to try to do is just see what has to be true about these vectors if this is going to work. In this video, it's a big if. In the next video, we'll get a theorem, and the if will become a thus it is. Okay, very exciting. Okay. So what I'm going to do is I'm guessing that that's a solution to my linear system. So I'm simply going to see what happens if I plug this in to both sides of that equation. Okay. So if I look at the left-hand side, that's going to give me y prime. That's going to give me the derivative. So I'm taking the derivative with respect to t. Let me get a better marker here. Of e to the lambda t v naught plus the derivative with respect to t of t e to the lambda t v1. Now here, the only t's show up in this scalar valued function. V naught is just a constant vector. So I'm basically using the constant multiple rule here when I say this is going to be lambda e to the lambda t times v naught. Now, those of you who are used to doing calculus with vectors might feel very comfortable with that. If it looks a little weird, off to the side, I'm just going to do an illustration. Let's suppose I wanted to take the derivative of e to the 2t times the vector 3, 4. Now, what I've just said, according to this rule, is that should be 2e to the 2t times the vector 3, 4. Well, if I didn't feel comfortable doing that, I could work out that this is just 3 copies of e to the 2t, 4 copies of e to the 2t. And when I take the derivative component-wise, I'm going to get 6 copies of e to the 2t, 8 copies of e to the 2t. And notice, that's equivalent to, I could factor out a 2e to the 2t, and that's times 3, 4. Okay. So that does work. If my vector here doesn't have any t's in it, I can just treat it as a constant and use the constant multiple rule. Okay, so that was the derivative of this first piece. I'm going to use the same trick for this second piece. It's going to be the derivative of the function times v1. And for the derivative of the function, I'll need product rule. So the derivative of t is 1 times e to the lambda t plus lambda t e to the lambda t. That's just t times lambda e to the lambda t. Excellent. I'm going to just distribute this out. So I've got lambda e to the lambda t v naught plus e to the lambda t v1 plus lambda t e to the lambda t v1. So that's what I get on the left-hand side of my differential equation if I plug in something that looks like this. Okay, on the right-hand side, what I'm going to get is a times e to the lambda t v naught plus t e to the lambda t v1. Now, the matrix multiplication distributes, so that's a copies of e to the lambda t v naught plus a copies of t e to the lambda t v1. And then scalars pull through. And that's true whether it's an actual constant scalar or just a scalar valued function. So this is going to be e to the lambda t times a v naught plus t e to the lambda t times a v1. Okay, so that's what I have on my left and my right hand sides at this point. Let's see. So I'll keep this up. Down here, this was what the left-hand side simplified to, and then here was what the right-hand side was. Now, I'm just going to classify the terms based on where t shows up. I have two types of terms. I've got terms that involve an e to the lambda t, and that's the only place where t shows up. So I've got those terms. And then I've got terms that have a t, e to the lambda t, in them. Everything else here is constant, so I can classify all of my terms that way. Now, if I look at the left-hand side, the terms that have an e to the lambda t in them, and that's the only place where t shows up, is this term and this term. So if I look at how many copies of e to the lambda t I have here, it's being multiplied by lambda times v naught plus v1. And on the right-hand side, this is the only term I have where the only place t shows up is in the e to the lambda t, and that's a v naught. So if this is going to work, that equation has to be true. Now, what I can do then is I can solve for v1. That means that v1 is going to equal a v naught minus lambda v naught, which I can say is a minus lambda I times v naught. So I can describe this vector v1, as I said, in terms of this vector. So even though we theoretically had two unknown vectors, once I know one of them, the other one is completely determined. Okay. If I look at the t, e to the lambda t terms, on the left-hand side, that was this, and what I had was lambda copies of v1. That was what was multiplied by t e to the lambda t. On the right-hand side, that's this piece, and that's got to be a times v1. Now that's a very special equation. Multiplying v1 by a is the same as multiplying it by lambda. Cool. That almost tells me that v1 is an eigenvector. It doesn't quite. If you want, you can pause the video and see if you can figure out what the other possibility is. Welcome back. Okay. The other possibility is that v1 could be 0, because this equation will be true if v1 is 0. So this tells me that either v1 is an eigenvector or v1 is the 0 vector. One of those two things has to be true. Okay. All right. I can also do one more thing, and that's I can figure out what v naught, how to describe v naught. It's not just, well, it kind of is something I can pick from thin air, but it has a meaning in relation to the other, the rest of things. Notice, if I were to plug in 0 for t, that would completely kill off this term. So notice that y evaluated at 0 is equal to e to the 0 times v naught plus 0. Because if I'm plugging in 0 for t, that kills off this term. So that's just v naught. Okay. So if this is going to work, v naught has to be what I'm going to call x naught, y naught, which is just the x value at time 0, the y value at time 0. It has to be the vector corresponding to my initial condition. kind of cool. Okay. So I can now modify my guess just a little bit to say that I'm thinking that the general solution will be of this form. E to the lambda t times v naught, where v naught is the vector corresponding to the initial condition, plus t e to the lambda t times a minus lambda I v naught, because that's what we said that our v1 was supposed to be. And also, if this is going to work, this thing has to either be 0 or an eigenvector. So that's a lot of conditions, but we've modified our guess a little bit so that we've gotten it down to, if I know the initial condition, I can put together this thing completely. It's completely determined. So when we come back, we'll have a theorem that'll tell us that, yep, it works. It's very cool. See you then.